And here's a planning problem. Okay. The planning problem look almost the same, except that now we add Z. Okay, everybody's going to trade on Z now. This one looks similar, except we have C. This one looks similar, except we have Z. Okay, I think I need C here. It's a typo. And this is again the same. You want to take action A, it's better than don't take action A. And this is the resource constraint. I kind of emphasize on this because it's come back to your point, how can I get the price? It's going to be the Lagrange multiplier of this. Okay? It's like how much output I have, how much consumption I don't have, tell me what the price should look like. And more important, and importantly, remember this, notice that this doesn't sum over Z. Because I assume that once you are in one island, you cannot trade with the other. I have to make sure that the market clearing happens within the island. So that's why I cannot sum over Z. So this has to be, sorry, for all Z. Okay? Each Z you have each island, one by one. Okay? And that is going to play a role when we talk about how many islands we should show up. Because what happened is, this one kind of tells you that there's no transfer across island. So that means you kind of limit the insurance across island. This guy here cannot insure that guy there, or vice versa. Okay? So that's going to be the cost of having multiple islands. But that's going to be benefit too, otherwise they wouldn't do it. And just go quickly. We have all welfare theorem, first, second, and existence theorem. I mean, the proof is very similar to what Prescott, the Sun, and Townsend has in 2006 paper. I mean, I have to say the Sun because they're two Prescott and the same name. Okay. I'm not going to go through that except you have questions. So the idea is because now we allow people to trade in the commodity that caused the problem, we kind of solve the problem. It's kind of cost theorem somehow. A bit different in just the sense that instead of talking just got a property right, we're talking about how we can decide the market institution or market-based solution for this problem. That's the only difference from cost. Okay. So now it's an example. Okay, it's still numerical. There's no empirical here. Let's consider this economy. This economy is going to give me unique price island, which is the one that if we have, we kind of doing okay. Okay, we have Q, 2Q, and just for simplicity, I assume very extreme. The Q are very perfectly correlated. Okay, the low output would be 0.1, the high output would be 1, and the probability is the opposite. If you take low action, very likely to get low output. Take high action, very likely to get high output. I mean, just make it extreme. That's all. I mean, you can make it less extreme than that if you want. Now the utility function. So here is going to be, there's going to be action here. There's going to be consumption 1 here and consumption 2 there. So the key is A interact with C1 only, not C2. So because, suppose if I put parentheses here, A interact with both of them, they're going to become partially separable. Then I don't have to do anything. Okay, that's why A has to enter the utility kind of asymmetrically. If it enters symmetrically across C1 and C2, it's going to be partially separable. And then we don't have a problem. And again, here we assume that gamma is 2.5. Okay, so here it's negative. So this is this utility when you get more A. Okay, is that okay? So this is kind of a utility that we're going to use. There's interaction between A and C1. That's going to show up in the results a little bit, but not for C2. Okay. But the key that I want to emphasize that gamma here is 2.5. Remember, gamma is tell you how risk averse the agent is, approximately. That's going to play a big role when we get the multiple island later. Okay, that's why I emphasize that. Let me show you first the first best world, variation equilibrium. It's the Adam-Smith world. Okay, everybody know everything. There's no private information. It looks like that. It's kind of strange a little bit here because even in the first best world here, we still want to randomize over action. We still want to put agent to work not so hard. That's because of the grid that we use. Okay, in this problem, it's primarily because of the grid that we use. Remember, here they can take A1, A equal to 1 or A equal to 3 only. Okay? Once, because the grid of the action force the planner to make someone work very little because that gives them more utility. If you make everybody work so hard, it's kind of too miserable for them, and you don't want to do that. That's why it show up here. It's not really a main point, but just want to emphasize that this is kind of a computation. I mean, it's not really numerical error because this is exact first best solution. I solve it by hand, but it show up because of the grid that I chose. Okay, but just want to keep you in mind also that here there's like 8% of people working little. Okay, and we will see how that happens when you have more constraints. Okay. And you can guess. Here is people who work less, right? A equal to 1. Okay, how many? Well, it's about like 12%. It's a lot more. So what happened is, here it's just a standard private information problem. Because you have incentive constraint, and incentive constraint make it harder for you to make people work, right? Therefore, you're going to let people work less more. I mean, let more people work less. Okay? It's a usual private information problem. Because you are more constrained. You cannot push them too much. Because you push them too much, they're not going to follow you. Okay? So that's why you have to let them you give them some slack.